Yeah, okay, so I'm wasting my time again with an AI. Let's just school. We need to tailor a series of was it the square root of 1 minus x? What was it? So it has the square root of 1 minus x equals 1 minus x squared, x to the power of 3, and so on. And here we have 2, and then 8, and then 16. It's a weird jump with minuses. Okay, minus, 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 2, 8, 16. X squared, so that's correct. Let's add one more though. Client with the Taylor series is very accurate. All the way up till there. Correct. Which is logical because x is indeed very small. And I have x divided by 2 minus the square of x divided by 8 minus the cube of x divided by 16, and even 2 terms more. And now we want to substitute x equals this, which is 4 times c0 times c2 divided by the square of c1. So this 8 here is wrong. The computer can't calculate. It should be 4. That would be 4 to the power 3 divided by 16 is 4. Yeah, so this is minus, we keep that, c0, c2 divided by c1 squared, and then 4 divided by 2 is this 2. And here we have the square of that, so we get 4 squared, 16 divided by 8 is 2. That's this 2. And the c1 squared is to the power 4, so this is also correct. And this is to the power 3, so that it becomes a 6. These becomes 3's, and this must be a 4. Yeah. You can leave 2 terms off, I guess. So let's not add those 2 terms. And then we fill this in. Then the result is my approximated square root of 1 minus x. What I really want is 1 minus the square root. I don't need this anymore, do I? Well, maybe one more time actually. To check what the difference is now. Well, it's what? Still extremely accurate. So the last 2 terms are already hardly doing anything apparently. Okay, it is what it is, very accurate. Yeah. Okay, and then I'm gonna do 1 minus that. And then we do the Taylor series. Actually, I don't need to print this anymore. And Taylor series is now given. Just do the 1 minus that is, let's use more or less then. Alt top. Okay, to this. And that is the approximation, and then we want to multiply that with this. Well, lo and behold, this is correct. How is it possible? Why is this printing minus 5,000? It should also be minus 10. Minus a half, C1, C1, divided by C2, divided by C2, minus, minus. Why is there a minus there? Hence we lost just 15 minutes because of the typo there. Yeah, just a multiplication. You moron. This should have been a multiplication. Okay, so I think pretty much verified now that this one is correct. How do I get from here to there? Damn it. How the hell did I do that? Does not make any sense. Makes no sense. What is it doing here? Like magic. And incorrect. And it doesn't even see that it is incorrect. Why? So useless. Now here. Multiplying by minus a half C1 divided by C2. Oh, that removes this. Well, but wait a minute. Okay, maybe I'm seeing it. So this thing turns into this. So we have S divided by 2. This divided by 2 is 2 times C0 C2 divided by C1 squared. If you multiply that with this, then the 2 is removed and we get a minus sign, and the C2 is removed and one of the C1s is removed. So you end up with minus C0 divided by C1. And this is actually correct. And then the rest of the series, therefore, must be divided by S divided by 2. In other words, the S squared becomes S, and that becomes that, and that becomes that. And it magically produces a new term out of nowhere. And the 8 becomes 4, the 16. It completely lost what it's doing here. Yep. Well, this one is just still correct. 128 divided by 2. 64. Yeah, this should be an 8. It's not good with calculating stuff. But it did give me a vague idea here. Yes. Let's try that again. So we have this Taylor series. Which is the square root of 1 minus x. And then we substitute x with s. And then we do 1 minus that. And then we multiply that with something such that, well, you just take s divided by 2 out of it, I guess. This equals s divided by 2 times 1 plus s divided by 4 plus s squared divided by 8 plus 5 times s to the power 3 divided by 64. Plus 7 s to the power 4 divided by 128 plus something of the order of s to the power 5. And now we see where it came from. So the quarter here is that this 4 and this 8 is 8th here. So yes, now I can continue. If I wanted to or have to or whatever. So this is something times, I can remember that right, something times S. Where the something is a quarter. Yeah, I'll just have to write that as 1 divided by 4, I suppose. So this is plus a quarter times S. And this is must be 1/8 then. And I want that to change to 1 divided by 0.4. No, not 1, 0.1. But same thing. And then we have something that is pretty nice. It does already have 5 digits, 6 digits, position. Okay. is kind of not true anymore, is it? It was an attempt, but no. No, it's not true. I think it's not true. Yeah, that story. I still might need it. This is not universal or true. This is different than what I had before. I think this was only necessary for approximating the Taylor series of the square root. So the other thing probably also still holds. So in the case that C2 equals 0, then this is definitely less than a tenth. It's namely 0. And then, yeah, this becomes 0. So this becomes minus C0 divided by C1, which is then exact. And if this is not less than 0.1, then we definitely have a not 0 C2. So then I might as well use my earlier approximation. Or turn that around. Random cubics. You should calculate this. That is why I don't have a gold. No, this one. Yeah. Yeah. Didn't do anything. With respect to the new cubic that I wanted to work on really. Where's my Discord? Mm-hmm. I will show what the problem is. So I have been writing this program which generates random cubics and then tests that d is less than 0, and the epsilon, the other thing, is a lot. If it is if it is less than 0, then we can't even calculate it, and this is not a number. And otherwise, if it's not less than 1, then yeah, forget it. And otherwise, we are going to use. So otherwise would be here. We are going to use a different algorithm, and then the question is, if that new algorithm works, then what cubics are still left that will fail? Failing being they are inaccurate with the current algorithm. And that means if we are more than 13 next after steps, so that double precision bit, totally significant double precision bit away. 13 is not that much, of course, but still. Then you draw it. And it turns out to be a very specific class of cubics that still goes wrong then. So these are all okay. And now we found one. Oh! That's not what I had expected. That's strange. Yeah, well, it definitely does not have a 0 close to 0. I guess the 0 is like here, which is not on top of 0. Let's go to the next one. No, that's more like it. This is what I expected to see. So the problem here is that the 0, the y is 0, this is a 0, that is a 0. But there is a 0, this 0, that has, what the cube is just touching the line. So really there's probably two zeros here very close to each other. And that gives a problem in calculating it. So we get something that is inaccurate. What it does is first calculates this 0. Then we do a long division of the cubic by x minus this 0, resulting in a quadratic, which gives the remaining two zeros. Solve the quadratic, and then I do one iteration or even 2 iterations. I'm not even sure what I left it at, of Newton-Raphson, and still we are 13 steps off. So it's still not 100% accurate. And the reason is obviously because the derivative here is almost 0. The thing is almost horizontal. So Newton-Raphson, I mean, it's debatable. I mean, the absolute value of this root is more or less the same as the absolute value of that root. So it's not as bad as when this would also be 0. But somehow we still get, after the long division, we still get something that is not super accurate, I guess. And then there's 2 roots that are incredibly close to each other. And yeah, the Newton-Raphson just doesn't really work here. Not one iteration anyway. And then you see, again, the problem is simply that the root, if the root is basically a touching maximum or minimum of the cubic, it just goes through it probably. I mean, it's a random thing, so I think we have 2 roots. So you can see it here. So you have 2 roots that are almost the same. In the graph, it looks like they're the same, but they are usually a little bit different. So we need a special algorithm. So again, just touching the y equals 0. And again, every time it goes wrong, it's of this type. Which means that if I make an algorithm that is good at solving the roots of this type, then maybe there is nothing left that is inaccurate, because all of them are like this, except this one. I don't know what's going on here. Maybe we'll still be left with this one then. Yeah, because this is definitely not of that type. I don't know why this one is going wrong. I have no clue. I guess you just have to say there's a lot of these. Okay, so I'm going to fix this, and then we'll see if there is still any left that are inaccurate. If at some point I don't get any inaccurate roots anymore with my algorithm for, say, 100 million random cubics, and yeah, I'm gonna call it a day or a month. Yeah, it's also a different type. Well, the derivative is 0, more or less. So maybe it's not that different. If you zoom out very far from this one, it also looks like that. So it just goes flat here and then goes up again. This is definitely something else. Saw this one before. Looks like have some kind of other characteristic. I suspect that the problem with this one is that the cubic term, so the x to the power of 3, is important in the root. That's my feeling. Which is usually the case if the thing is just very steep. So like this is steep, and then you have a little kink, and then it goes up again. And this is just a very important term. And if that just happens around where the 0 happens, then it also requires some more attention. Those are all of that other type. Touching local extreme. You can actually see that it goes through it. It's 1 pixel higher here than the y equals 0 axis. The x-axis. Yeah, and here we have that thing again. So narrow, steep. That's another one. Well, that were 100 million, I think. Not even sure. Let's see how many we had. Good. Number of cubics. Oh, only 1,000,000. Oh. Okay. I can use ChatGPT for the formatting of my math formulas. Maybe this thing makes a tiny little bit less errors. Okay, let me think. So we have I did it before already on Discord actually. We have this cubic with derivative So we set this thing equal to 0, then yeah, you can also write it as this. I think I divided it by 2C3. I just did that to be able to apply the solution formula for a quadratic directly. This is now simply minus b plus or minus the square root of b squared minus 4 times ac. So 4, a half drops here and a half drops there. And you just end up with 3 times that for the 4CA, 4AC, I mean. And then divided by 2A, so 2 times this, just that 3 is remaining. So this E, or this formula, gives me the two local extrema if they exist. So I'm going to assume that they exist. In other words, that this is larger than 0. Okay, I've done a little bit more on Discord, but need to stop here for now. So this is still exact. I just did a substitution. But yeah, if t minus e is a root, or is is a root, then no, sorry, that's not true. If the root is close to e, then t must be very small. So we could find t then in by setting the first three terms to 0, and already neglecting that one, which then can be easily solved because this is a quadratic. But at the moment I'm more concerned with the point at which this can be assumed. Yeah. So before I had an x-axis scaling, and then we demand that the formula or the expression that decides if we can apply this approximation should not depend on that scaling. Oh, I forgot how I did that though. Because I can do the same thing. We just introduce an abstract d, which has the same dimension as x. And then I do another substitution for the root to be equal to, let's see, yeah, d times some epsilon. And then we have to demand that epsilon is much less than 1. So do we formulate that? Maybe first let us think about this. Probably can't even do that. Yeah. That's why I call it a waste of time. Breaking down the encouragement. This is being sarcastic here. Right, no, so Oh no idea why I keep using symbols that I don't have here. Should just copy them. Okay, let's do that. As in, oh, I have it. Absolute value of t. This is about the absolute values. Okay, so divided by d squared and divided by c3. We have left c2 divided by c3 minus 3 dot e. Is that correct? Yeah. Yeah. Well, that could be problematic then. If 3e equals c2 divided by c3, or is in the neighborhood of that. Then the right hand side becomes arbitrarily small. Except of course that we set d equal to that thing. Yeah, still not quite right. I mean, this only guarantees that this term... Oh, something disappeared here. What was here? Just C3, I think. No. It was C3 times t to the power 3. There's a d to the power 3 missing. Yeah, this is the whole thing. C3 times and all out of that thing, okay? It's getting such a mess. Why is it getting such a big mess? So we'd continue with this constraint or something in mind. We can neglect the last term and solve I want to go back to t. How to get my epsilon? Epsilon is t divided by d. So let's just write epsilon here. T divided by d. And the t is u here. Which then gives me Is this true? U is divided by that. Yeah. Not so happy that I have to calculate U before I even know if it is usable. You have to first calculate it and then divide it, and then if it turns out not to be less than 1 or much less than a tenth or something, and we did it all for nothing. Yeah, I think I'm gonna call it a day. Shall we ask a question or just dump this on ChatGPT? No, it can't do math, so I don't care. I'm just dumping in here to get some archive. Let's play chess. My rating has dropped again from 2050 or so. Uh-oh, I lost the pawn. Yeah, no, he doesn't see it. I think you can just take here. And then if I take the bishop, continue taking. Pretty sure of that. Let's go here to solve that problem. It's not really solved, but only solved I could take back with my knight. So he takes a pawn, I take a knight, and then he has a fork. Okay, but that fork is not attacking my queen, so then I can take here. Takes back. Fork is still there though. Yeah, it was, I don't know. Feels perfectly okay. Though any sane person would have moved the bishop back first, which I only now realize. Shall I sacrifice something? Let's say take the bishop, take here. Can't defend that, so I'm gonna win 3 pawns unless pushes it. I could then, yeah, I don't like that. I could go here. They push, my knight goes there. He takes still the same thing. Yeah, I would rather keep an eye on this one. Do. But if we go back, they pushes, the knight moves, and then this one falls with attack on the queen. So you go back, and they push. I would have to take the knight first. So I take a knight, they take a knight. I take a bishop, piece ahead. They take a queen, I take a queen. They take my, there's no pawn. And then there's a pawn here, which I'm going to win. I think I'm going to try this. Can this go wrong? Probably. Yeah, so now I have to take here then. Oh, this was, yeah, no, it's possible, yeah. I thought it didn't work. Uh-oh. Okay, so now you have to move the knights and just go here, I suppose. Takes this one. This pawn needs to be pushed. Yeah, I think so. Wait a minute. What about this pawn? Trapped bishop. Not really. I can go here. Still. Just going to develop here. Just go away from this diagonal. I mean, that doesn't hurt. This looks a bit scary, but I have 3 pieces. Oh, yeah, 1, 2, 3. Can put a pawn here. Even if it just first is. Still nothing. Does he threaten anything? Not really. So now I could push this. The why not move? I mean, I wanted to do that. Can't take with the knight now, though. So I take with the rook and the knight comes here. Yeah, I just take it. No problem. Going to lose a tempo, though. Have to move the rook away again. Yeah, black doesn't have any moves left, so I shouldn't worry about losing tempos. I could put the bishop here. That is true. Oh, the bishop goes there. Yeah, okay. So I don't see the danger whatsoever, really. Oh, there is a danger though. Yeah, there's definitely a danger. If the bishop comes here, no, I just take it. Well, then he takes my knight currently. I have to go here. Oh, I don't have time left. Oh shit, no time. Oh, I'm losing a rook. I totally missed that one. No, I have no time left, and I'm 2 points down. Damn it. I give away this bishop because I don't have time left. Take the bishop. Yeah, he doesn't see it. Okay, I'm gonna go for the door here because I don't feel very nice about this. I don't feel very secure. It's cost still a point, but otherwise, let's see if we had something here. So I wanted to go for the draw anyway, but then he moved his knight here, so now I can't. Give away the rook and I give a check, it just puts the knight in front of it. So I thought I'd do this and he probably takes my bishop. But was it good? Yeah, it was good. I'm minus 3.6. So it was a nice trap. Basically a poisoned bishop. Double question mark. Yeah. I'm happy with the draw. I'm gonna do this puzzle here. Puzzle of the really the everything wins move? No. What? Can win the knight. No, it's nonsense. Can't count this as a queen. And he's very hard. So was it take, 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 take? Threatening to win the queen in 2 ways. So the queen has to move, can't give check, can't defend the knight, except by going here, and then I win the queen also. But the queen goes somewhere else. Actually, where does the queen go? I could go here maybe. I can give check, but then the queen takes both. That would not work. Maybe I should just give check. Nah. Nah, no. Can't be it, right? That can't be it. No, it has to go mate, I think. I have to give a mate, otherwise I'm down way too much. No, man. Possible. Going here looks like reasonable, because that one is defended. And I'm attacking this one twice, and I'm standing on this diagonal, threatening to give a check here. But you can just take my rook, and have to take it back. And then they give a fork here with the queen, on my queen and king. I'm so dead. Yeah, incredibly dead. Well, they defended it anyway. Check, you go here, take mate. That's not good. It's like I really have to give check. Or take the queen. One of them. If I give check like this, then I still have nothing. This mate threat here is not even using this queen. So good check goes forward and just take the queen. Well, they could take my queen, I still have nothing. Or take my rook. Then I have to take. And then comes the knight, and I have to give my queen. I could give the queen then. Nah, I'm gonna take the queen. It's probably wrong, but I don't see anything else. Yeah, it's a good move. Great. But yeah, now if I just take the rook and they move the queen somewhere. Where are they going to move the queen? Yes. I mean, even if I get both the rook and the knight, which I saw in the beginning, is that enough? Well, maybe it is enough. I have a rook, a bishop and a knight against the queen. But it's not winning. No, I mean, what other move is there except giving check first? So it's again taking the knight or give check. If I get check, it just goes forward. Then I have nothing. I can't even take here then. Can't just everything is checked. I have to take the rook. And that's not a move. You gotta be kidding me. Check does wins, you say? How? No, it doesn't. Which check? This one? Oh, and then take the queen. Yeah. Fuck me. Yeah, now we'll piece up. That was the solution. Yep. Extremely time to go to bed. See, minus 27. That's a whole lot. I'm gonna go. What? Wait a minute. What does this thing say? Do you see what it is doing here? It's fucking up again. Oh, wait a minute. I confused this E with an epsilon. Never mind. Never mind. Yeah, so then dsc divided by c3. Okay. Yeah, it's just summarizing what I said. I'm hesitant to give a thumbs up because I think at the very least it should have said here then this ensures that the term is negligible relative to the quadratic term if epsilon is much less than 1. It says that here. But yeah, I was missing it. Here. It says that dot. Plus it's just an summarization of what I said anyway. Right then, yeah. Good night.